This is part 2 of this video series looking at how the Tessent tools account for the full fault coverage in complex SoC designs. In the first part of the video series, we looked at a high-level overview of the tool capabilities that enable the fault coverage counting. What I want to do in this second part of the series is to demonstrate for you how to actually use the tool for reporting coverage information when working inside one of the cores that will be incorporated into an SoC design. So first, a brief description of the core design we'll be looking at. It is a wrapped core, so we will be using hierarchical DFT techniques. This means we'll be performing ATPG at this hierarchical level with the wrapper chains configured for in-test mode operation. The resulting patterns will be saved and ultimately retargeted once we get to the SoC level. In addition to this being a wrapped core, we also inserted several DFT instruments earlier in the flow at the RTL level. These include MBIST, in-on-chip clock controller, and the IJ tag network and infrastructure to control these instruments. So what I'll do now is I'll switch over to a Linux window and start running the ATPG tool after all the insertion has been done so we can see what the coverage reporting looks like. The first command here is set tsdb output directory. So right now what we're doing is we're telling the tool that we're giving it a destination directory for tsdb information as we go forward. The next command here is this read design. So when we redesign for, in this case, the processor core, we give it a design ID, which is a view. It could be an RTL level view. It could be a modified RTL level view. In this case, we're pointing to the gate level view, so it's the gate level scan inserted netlist that we use for ATPG. But as part of redesign, not only are we loading in a particular gate level netlist, but we're finding the ICL view in the Tessent environment. Now, in this ICL view is essentially represents what we inserted for IJ tag controlled instruments. In this case, things like the MBIST controller, OCC, and the IJ tag network. So this is what allows us to go find some of this fault information, which I'll show you as we go forward. Now, I've already partially run this ATPG script, and I've gone through all the DRCs, and I've gone to transition to analysis mode, and then very quickly just did add faults -all. So I'm adding the fault population, and then I'm going to report the statistics. All right, this is even before we generate any patterns. And when we report the statistics, in this case, we're looking at transition faults. But even just by virtue of static analysis, simulating our test setup information, and also reading some of this default information from the JTAG instruments, we can already classify a significant number of the faults. So for example, here are all your major fault categories right here. And then for some of these fault subclasses, both the DI, detected by implication, and the ATPG untestable, we have this separate panel of information where we can provide a more detailed breakdown for DI and AU. So for instance, what we've been able to do by virtue of loading that ICL view, we can recognize already the fault status for some of the IJ tag related faults. So we know right away that a certain number of faults are going to be ATPG untestable. And same thing for the on-chip clock controller. There's a certain number of faults there that we know will be ATPG untestable. So now we've pre-categorized those faults. ATPG is not going to look at them. But not only do we know that it's undetected, we know what part of the design represents those AU faults. And if we look at the detected by implication category, we can see that there's MBIST related faults here. So again, these are certain faults related to the MBIST logic, but it's, I think, important to point out that we're not looking at faults that are in the MBIST controller. So these are really more faults between the MBIST controller and the memory themselves. So one thing we can do is actually take a look at the specific faults here. If we want to get a handle on the types of faults that this represents, we can do a quick report faults dash class and give it the di.mbist category. Okay, and we can actually see that for all these DI MBIST faults, These are specifically pins like the Q, the output pins of the memories themselves, the D inputs, and address pins. So these are actually the pins of the memory itself that, because they get tested as part of the memory BIST test, these faults will have been detected. If we open Visualizer here, now we can look at it in terms of the hierarchy. So we have our hierarchy browser, and then we can actually take a look at analyzing the fault coverage. The things that we're kind of looking at in terms of detail, the AU faults was one of those categories. And then you can actually add to that a different category. Let's look at the DI faults. All right, so now we have AU and DI. And you can see this little expansion, this little arrow, two-way arrow here. If you click on that, what we're doing now is we can expand the AU category and show all the subcategories. And here you can see where we have the OCC and IJTAG instruments there, which is what we looked at previously in the command line view. So we can collapse that. And then you can also do the same thing in terms of the DI faults, for instance, detected by implication. And again, here's the MBIST related fault. From here, we can go ahead and create the patterns. But we don't need to sit around to run through that entire ATPG run. But what I want to do is point out maybe one other additional command here that is important to what we're trying to do overall, not just here at the core level, but eventually the SoC level. And that's here. After you've finished creating your patterns, one of the last things that you will do is to write TSDB data. So with this particular command, write TSDB data, we're going to store the TCD file, the Tessent core description file that represents the setup for this ATPG run. We save the flat model. The flat model can be used for doing diagnosis in particular later on. We'll save the fault list, which is an important piece of what we'll demonstrate in the video 3 or part 3 of this video series. And then the patdb format of the patterns. So all of that is done by this one particular command. In summary, test coverage information in the form of either DI or AU faults is forwarded to the ATPG step from the insertion steps when you execute that redesign command. Tessent Shell is able to automatically retrieve this information from the TSDB, as well as store additional information from the ATPG step for retrieval later at the SoC level. The resulting coverage is achieved more quickly because more faults are pre-sorted into appropriate categories before ATPG even starts. The results are more accurate, especially in the case of DI faults that would otherwise be considered AU. And the report breaks down these fault categories into finer details so you can quickly identify the reasons for these results and determine if anything is actionable. So thank you for your attention and for taking the time to watch this video. Please be sure to watch part 3 in this series, in which I'll do a similar demonstration of fault coverage reporting, but at the SoC level, consisting of several wrapped cores.